Hey guys, hope you've all been well. Apologies for the delay. I know that there's been quite a lot of a demand as to where the next N20 video is going to come along. Today's the day. I now have, I guess, the third installment in the series. Obviously, this is more talking about, I guess, our Darton Wet Sleeve solution and where they are up to in terms of the installation phase for the motor. And we have 3 engines right now currently with Brintech. We've done quite a lot of work with Brintech. They've been absolutely fabulous to work with. And we are extremely confident now that we have a product that is pretty much something that we think could compete for the likes of World Time Attack. It's over-engineered for a lot of people, but unfortunately from what we've seen, there's not a lot of sort of intermediate options that are going to be reliable long term, right? We've already looked at flange sleeves, we've looked at parallel sleeves, we've seen multiple issues with parallel sleeves dropping. Now, I know a lot of that can come down to installation, but the problem is that a lot of shops don't understand, I guess, the importance of getting it right on this engine specifically. If it's not dropping, we've had issues with coolant leaking because of the passages between the cylinders. The sleeves have been sort of not right in terms of their diameter, and when they've been machined in, they've breached coolant and they haven't been sealed properly, and we've had coolant issues. And I know a lot of this can come down to workmanship. The problem is, though, is that a lot of shops just don't seem to get it right. So to try and remove them from the equation of having your expensive built motor, we've gone ahead and actually just engineered a complete solution that that adds in closed decking, and it's a wet sleeve design as well, which means that we completely remove the factory cylinder, and it also allows us to run thicker wall material as well, which allows our sleeves to be a lot stronger than any other sleeve solution on the market. I mean, for example, around the thrust surfaces of the sleeve. Now, for those that don't know, the thrust surfaces, the sort of top portion of the sleeve. If you have the engine block, say, and you've got cylinders, you're looking at it dead on, cylinders 1, 2, 3, and 4, right? You've got your intake on the right-hand side of the N20 because cylinder 1's at the front. You've got your exhaust on the left side, okay? Your thrust surfaces are essentially, if you think about it, it's your intake and then your exhaust. So you've got a thrust and a non-thrust. Now, the thrust side is essentially the side where the piston and conrod begin to move down after the combustion process. And then your non-thrust is the opposing side of that. It's those sections of the sleeve, essentially, of the cylinder where it takes the most abuse. So you want it to be as thick as possible in that area. The thickness of the sleeve between cylinders doesn't matter a whole lot in this region, but it's still important, bearing in mind it is important, but it's not as important as those other two surfaces, right? Because the conrod is not, rotating, I guess front to back. It's rotating, left to right or right to left, depending on your engine configuration and how you're looking at the engine. So we're running in the thrust surface, we're running around between, I'm not going to give the official number because obviously being it's our IP, I can't give away those specs, but it's between 8 and 9 millimeters of thickness on the sleeve. And then between cylinders, we're running the maximum you can, 3.5 mil, because the bore spacing of the N20 makes it incredibly difficult to run anything thicker. BMW's pretty much runs the same bore spacing on pretty much all of their engines, 91 millimeters. So that's center to center. So if you have cylinders 1 and 2, for example, and let's say the center of the cylinder is here and here, it's 91 millimeters apart from each center to center. So then if you work out like the size of the bore for the piston, so if it's 84 mil, it gives you about 7 millimeters total thickness between each cylinder, but then each cylinder has about 3.5, right? So collectively it's 7, but divide that by 2, it's 3.5 millimeters. So when it comes to adding in these sleeves, we removed the coolant passage between cylinders, pretty much removed it. We did leave a 0.5 millimeter passage, which, I mean, it's not a lot, and it's quite small, and we've actually moved it down a bit in the cylinder, so it's not as high up and close to that sort of thrust and non-thrust sort of areas. We try and give us more thickness where we could have it. And we've spent a lot of time with the lock on the machine, on the CNC machine, trying to get our machining correct, get our programs correct. And now we have something that, is finalized, and something that does work, and it goes in, it fits like a glove. The machining is all done to a 1 to 2 thou tolerance. That's what Darton recommends. We did it on a 3-axis CNC, which is pretty much the minimum you can install these sleeves on. You can't use a honing or boring machine, especially because we're not, machining, I guess, circular sort of shapes where, partial circular and a little bit of flat here and there. So we need a CNC machine for what we're doing, basically. Now, we have seen some success with flange liners, and we have seen some failures with flange liners. Notably, I'll chuck some photos up now, actually, of an example of flange liners that was unable to sort of handle the 33 psi and give or take 400 horsepower in dynojet standards. Now, granted, this car did have some issues with the fuel pump giving up on itself, and we had a lot of lean conditions. But the problem, I guess, is that the sleeves cracked, and they shouldn't have cracked. Now, I know, okay, you could argue it was pretty extreme sort of event, and the sleeves cracked. Maybe if that didn't happen, the sleeves wouldn't have cracked, and you're correct. But the thing is that when you go and build an engine, you're not building an engine to just move that failure point to the next goalpost, right? It's not like you're just moving the goalpost every time. When you build an engine, you're expecting, or you'd like to rather, to build in a safety net, right? So room for error, margin for error, right? Say you want to build the motor to make 450 horsepower, you build it for 600, right? You want to make 600, you build it for 700. Like you build in that room for error, so that if things do go wrong, you have hopefully the strength of the internal components to withstand any out of the ordinary abuse that might occur. The problem we had is the sleeves we had installed really were not designed for anything more than what we were actually asking from it. So when push come to shove, they ended up cracking. They weren't thick enough for our application. They were flange sleeves, which is good because it solves pretty much all the problem of dropping. It did solve our problem of not breaching the coolant passage between cylinders because they weren't too thick, or the wall clearance, essentially, the wall thickness on the sleeve wasn't too big. The next problem you have too is that flange sleeves might solve one problem, but then you still have an open deck, right? Now, you can obviously close the deck, but if you look at the cost to close the deck and then the cost to install flange sleeves, we've actually got it to the point now where that's the exact same cost as it is to install our Darton wet sleeve solution, which incorporates all of that. Which is why we recommend it. Not only are you getting thicker and stronger cylinders that can take way more abuse. I mean, we have designed this and we anticipate a minimum of 1,000 horsepower, right? Darton runs actually quite thinner sleeves to what we have designed on their B16 Hondas, and they make well over 1,000 horsepower, 1,000 to 1,200, and they're pretty happy. So if you look at that, it's pretty tried and true tested technology. Their material is quite unique. It's quite strong and robust. They've been extremely helpful through the design process. I've gone through in CAD and I've done all the drawings and designs. I've had some help from Brintech with some of the design cross-referencing and making sure that we're being considerate in certain areas of the engine block and making sure we're adding strength where we need to. And then relaying that information with Darton, and Darton have been extremely helpful with giving us some advice as well. So all in all, we've worked with quite a number of people, including our machinist Jeremy and some of our other local resources around Brintech to sort of help bring everything together from a machining perspective. So a mammoth effort involved, but we have something totally unique. No one in the world has Darton wet sleeves in an N20. The world record N20, for reference, has Darton flange sleeves. It is open deck. It is making a lot of power. Now, why hasn't that failed? Well, I'll give you a few examples. One, they were correctly designed flange sleeves. Two, we're not running a lot of boost. We actually have a very good turbo setup for that car, which we've been very fortunate. We're running 34, 35 PSI, thereabouts. And the way that engine has been assembled and prepped, the guys over in South Africa have done a really good job over at Bundler Motorsport of putting that engine together, and we haven't had issues from a block perspective. Now, it is a bit early to tell. We intend for this engine to survive and keep going. The problem is, though, is that being on the dyno and getting a power figure on the dyno is one thing, right? It's a controlled environment. You go out and say you do rallycross, this engine may fail, right? That's why it's hard for, say, the likes of CP Carrillo to rate conrods for a certain amount of horsepower, because that horsepower can vary greatly depending on your application, street, drag, rallycross, motor carnival, like all those different events, they put so many different forces on an engine. You might have a conrod that can take 1,000 horsepower in a drag situation, but you go and put it into a rallycross event and it can do 300 before it starts to break and fail. So it's not always as simple as, I just want to build my motor and I slap this big, Garrett turbo on it and call it a day. No, you need to take a very careful and considerate approach, because the components that you put into an engine will dictate how that engine survives, how much power it can make. Like I said, when you build these motors, you want to build them for a 20%, 15% sort of margin of error, right? Overbuild it so you never have to build it. We are already tuning the stock engines, well over what the manufacturer rates it. And whilst we know, on paper, the maximum power that those rods could handle is about 400 to 420 wheel horsepower based on Dynojet figures. And as long as torque is under 550 Newton meters at the crank, that's what the numbers say. In theory, not a lot of that has been tested properly, but we have a lot of reliable data with cars making between 360 and 380 wheel horsepower. The biggest reasons why a lot of the N20s fail getting even remotely close to 400 comes down to actually quite a few things I can name on my fingers, right? So number one, poor servicing. Now, a lot of people will think they're doing the right servicing, and it's not always the owner of the car that has made a mistake at some point in the engine servicing. It might be the previous owner, or it might be the mechanic cutting corners, or maybe they just forgot. We're all human, right? People can make mistakes. The N20 needs to be serviced very, very carefully. You need to have the right components installed, the right mods, the right tune, and on top of that, you need to have the right turbo. A lot of the turbo options out there just aren't right. They might make some power. If anything, they make a lot more torque, and torque is where this engine falls over, right? Torque adds heat, torque adds stress. These turbos peak torque really low in the RPM band. They stress these motors out very quickly. So if you don't have the right tune that doesn't make a very linear sort of torque and power band, you run very good risk of the thing falling apart and breaking. A lot of this can be avoided. Unfortunately, some cars fare better than others. It is a luck of the draw, unfortunately, in N20. As much as I love the platform, it is one of the most unreliable engines in retrospect to other turbo BMW motors. I mean, especially if you're going to compare it against the B48. That doesn't mean it's bad. It just means you need to pay very careful attention to this platform to make sure it lasts forever. I mean, the SR20 is a great cross-reference example. It's actually fundamentally not that much different from the N20 in terms of its reliability, stock, what power you can get out of that engine, stock, contrasting to what the N20 can make. Like, yeah, okay, it might make a bit more torque, but the power limitations are the same. And torque can also depend on your gearbox ratios too. Let's not forget that, depending on how you're measuring it, of course. But it's a good contrast. But why is the SR20 still really popular if it can be a little bit unreliable stock? Well, one, it's JDM, and there's a huge scene around the whole Sylvia and the whole drift scene, right? So it's exploded, but it's also been a really rewarding engine for people that have looked after it. They love it. All right, it's 4-cylinder, it goes hard. Slap a turbo on it. There's heaps of mod opportunities now because it's nearing 30-ish years old. Like it's been around. There's a lot of development. A lot of people now know what you do and don't do with that motor. It's the same here with the N20, right? We're now 10 years into its release cycle. And I mean, pretty much Navardi Tuned has been the only ones in the last 4 and a bit years now to actually do any development, any substantial development on this platform. No one else has even bothered to challenge us on this, really. We've had some products arrive that have had to be tweaked, whilst there is some carryover from the 6-cylinder. Unfortunately, it's not copy and paste. You can look at the spool pumps, for example. The FX150 doesn't work on the N20, and it's not that the pump is not reliable and the pump doesn't work. It's a fantastic pump. The problem is it just doesn't have enough ability to run high rail pressure for stock injectors. If you were to get the FX150 and put the upgraded S63 TU E5 injectors in, no problem. The problem is that it's an expensive pump, couple it with the injectors, And then the fact that most of these people that are running these sorts of upgrades are running, maybe stock turbo or maybe a stage 2 turbo. It's a lot of money to throw into a car for those types of gains. When you compare it to the B48 TU pump retrofit, which is nearly $1,000 cheaper, it makes it more compelling to go that route. It's not to say that these aftermarket pumps, Dorch and Spool, are terrible. It's just you have to be careful with the N20 on what mods and what path you go down, which is why we've made a wiki. It's why we made some infographics. I know they're a little basic, but they're designed to give you an opportunity to see what the bare minimum is to get your car on the right track. They're not supposed to be a gospel, but they are supposed to be a bare minimum guide to get your car to where they need to go. Anyway, I know we've talked a lot now, but what I will now do is I'll hand you over to Brintech. Brintech has put together a lovely 8-minute video for us explaining the sleeves in a little bit more detail, especially from their perspective of doing the install. I did the majority of the design work on it, but at the end of the day, the machinists and the engine builder, Tony, and everyone involved, they're the other cogs of this machine that have made this project happen, and credit where credit's due. They've all done a fantastic job. We are working on as well, it will be mentioned in the video, we are working on N55 ones. That is coming. The carryover from the N20 is like 98% the same. It's really good. It's really awesome. That's the case. That is coming. It's just time. Time at the moment, full on. We are full on at the moment. But without further ado, I'll send you over to Brintech.
G'day guys, today we're going to show you some N20 engine development that we've been working on for a customer of ours, Navardi Tuned, owned by a gentleman named Harry. So he's been working for some years on these N20 engines and developing them for his own car, and he's found some weaknesses and flaws in them, and we've gotten to the point now where we've come up with a final solution that should see this engine through for a good long robust life with high boost and high output, a lot more than what the engine was designed for. So a lot of people might say, well, why not just put a 6 in? But a lot of people like the 4-cylinder. They're lighter in the nose. There's a whole bunch of reasons people love these things. So we've helped Harry develop this engine. He's designed a liner from Darton sleeves in the US, which is one that I've got in my hand here. And today we're going to show you basically the process from a standard block, how it's machined to be able to install these guys, and what the benefits are of using it. So I'll let you hold that, Tony.
Yep.
Now, if we turn around and have a look behind you, we've got, here's a standard N20 block. So as you can see, it's an open deck design. About halfway down the liner, up to the top is the water jacket area, all through here. And they're an aluminium liner, of course, but they have a very thin iron liner on the top, which is, I think it's spray coated on, a twin arc spray system coats that on. So if you want to increase your piston to bore clearance or service the block, there's nothing you can really do, because once you take that steel out of there, you're into the aluminium and then it's useless. So come across to here, you can see a block that we've had machined. So we've taken out the top half of the liner down to the base of the water jacket, which is all in here. And we've taken some material out here to slide our liner in, which has some O-rings on it to seal the oil from the water. And we've done some machining around the deck here. And that's for the wings of the liner, which I'll just get that again and show you. So that just shows these wings here allow a tolerance fit of about 1/2 thou. So we cool this down and heat the block up to install it. And then when it all cools, it locks together. That then gives the liner stability compared to the standard liner, which doesn't have anything at all. So I'll hand this over to Tony and he can run through some technical about how this liner works and why it's so much better than a standard setup.
Okay, so yeah, we've ensured that we've got a interference from this these wings on the open deck sealing area there. That's going to give us that rigidity of the liner, so we won't see any movement there at the top of the bore due to pressure or force. We've also done a lot of intricate design work to retain as much material as we can around the stud holes, so that the gasket is sealing properly there, to reduce the prevalence of any coolant penetrating into those stud holes. And the pressure from the Cooper ring, the way that we've designed it is, the head's pulled down nice and tightly on the Cooper ring, and that force is going straight down to the bottom on this balcony seat here, which is the machine surface at the bottom of the bore. So it's a nice vertical, positive, broad seat contact area in the bottom here. And there you can see our 3 grooves for our sealing O-rings to separate the coolant area from the oil-wetted area in the bottom. You can see it's quite a rigid, thick, solid assembly. We've designed it so that we're getting minimal clearance between the liners, so we're keeping those clearances there nice and tight all the way through. And that fit is very precise, as I said, around here with the interference. So we've got to actually warm the block, and we cool the liners and get them in. And we think it's a pretty tight sort of a solution.
Yeah, so this block has the 10 head bolts that normally go in. The middle 6 are an M11 size bolt, and the outer 4 are an M10. So we actually drill and tap these out to an M11 as well. So we have 10 sets of M11 that we convert to a stud, and they're quite a long stud. They're probably about 250 mil long. They go really deep down into the block where the threads are. And the rest of the gasket is just here. Let's give you that, Tony. So that's the design of the gasket that we use on this engine. It's just a carbon composite gasket that has a bead installed on it. It just sits on the top like that. And then the floating fire rings just slot in the middle there. So you get a lot of clamping force on that because it's probably about 1.5 mil thick, the solid steel. And again, yeah, that just pushes directly on top of the liner to the second stage of the seat that we've machined out. Just have a look in this block here again for reference. Borrow that liner, please, Tony. So as Tony was saying, we sit down on this point here, which rests on this ledge here that we've machined out. So when the head goes on, we're clamping on this part of it. I'm not clamping here or the bottom, it's just this part here. So that's a nice strong way of holding the liner still, and then these steady it, as we said before, that way.
And you can see over here that perimeter seal on the gasket, where the sealant bead is around here. We've retained all of that area around there to maintain that seal consistency right through there. So we've done as much as we can with what's available to come up with this solution. I think it's going to be quite a good long-term, high power solution for these N20s.
Yeah, that's right. So we've got 3 of these that we're putting together at the moment, and Harry's talking with all you guys out there who want to do the same thing. Getting these liners is a bit of a wait. I think it's about 20 or 24 weeks at the moment to get these done. This has been prototyped and designed by Harry and Darton just for this engine. This is the first of its kind for this engine. So we're also looking to possibly be able to use these on an N55 engine as well, but we won't be able to get to that for a little while. So we're just concentrating on the N20s now because we have the product and we have a prototype put together. So we're going to now put this thing together and get it running pretty soon in a car here.
Oh, for aftermarket conrods, there's relieving at the bottom of the bore.
Oh yeah, let's flip that over and just show what has to be done.
Okay. So if you have a view down on that angle, on this side, you'll see that there's a bit of relieving to do there at the bottom. That's probably more than necessary, but that's just this prototype version. And yes, just be aware, and everybody that doesn't know, the crankshaft is offset to one side on the N20, like some other more modern engines as well. So that's the reason why you've got the notch on one side, not on both sides, because the actual crank offset is significant on this engine.
So we'll bring some more content to you guys just to show the product and result once it's all in, and hopefully we can lock this one down as being a good, robust option for the N20.